Good morning. Here, this is today's topic, wrong ideas about time and length. Yes, subject is physics, and I'm going to start a new chapter, that is special theory of relativity, given by Einstein in the year 1905. Okay, so to study that subject or that chapter, we have to start from the very beginning. We have to verify the truthfulness of the idea about space and time, and many other things are there. We have to re-investigate. Yes, we are in need to re-investigate whether those concepts which we are using are correct or not. Okay. So, how these ideas came into the mind of the scientists? I should rather say how this idea came into the mind of Einstein, only one scientist. Okay. So that's why I have written the heading to be, or the title to be, wrong ideas about time and length. Yes, still we have ideas about length and time, but those ideas are actually wrong. But in our daily lives, if we use those wrong ideas, still there is no problem. Yes, in spite of using wrong ideas, there is no problem at all. Yes, you will face problems if we use these wrong ideas in case of special cases, in the case of special things, such as high velocities which are comparable to the velocity of light. I am not talking about the velocity of an airplane, which is almost 850 km or 900 km per hour. I am not talking about the velocity of rockets. You know, those are having high speeds, but those high speeds are not comparable, or I should rather say this way, that those high speeds are very, very less than the speed of light. If speeds are very, very less than the speed of light, then our wrong ideas about space and time won't make any problem at all. But if speeds are very high, means 80% of the velocity of light, or 90% of the velocity of light, or 50% of the velocity of light, these velocities are comparable to the velocity of light. In those cases, you will face problem. What kind of problem you will face? The experimental result and the theoretical result won't match at all. There will be much discrepancy. Much discrepancy you will find. Okay. So let us start with the two terms are there, time and length. Let us start with time. So one experiment was done using high energy particle accelerator. Okay, one experiment was done using high energy particle accelerator, and as a fundamental particle, pion was used. Can you see? Pion, P-I-O-N, pion. Pion is also called pi meson. You know this thing, I think. In the subject of particle physics, you can learn all these things. Pion is also called pi meson, and you know that pions are of three types: positive pions, means positively charged pions, negatively charged pions, and neutral pions. But experiment was done using positively charged pions. Yes, there are differences between these types of pions, because there are three types of pions. When pion is at rest, so for charged pions, means positively charged pion and negatively charged pion, when the pion is at rest, the average lifetime of a pion is almost 26.0 nanosecond. Okay, 26.0 nanosecond. Nano means, you know, 10 to the power minus 9. This is the average lifetime of a charged pion, whether positively charged or negatively charged. Okay, and the experiment was done using charged pion. But for neutral pion, I should here mention that thing. For neutral pion, the average lifetime is much shorter than this time, 26 nanosecond. What is that time? That time is 85 AS, I have written in short, 85 attosecond. Atto means, you know, 10 to the power minus 18, 1 8, okay? 10 to the power minus 18, that is atto. So 85 attosecond is much less than this value, 26 nanosecond. So experiment was done using charged pion, okay? So actually this lecture is not on pion, this lecture is on time and length. So I am not going into the details of pion, or I am not going into the details of the experiment, okay? So one thing was done in length. So this is the lifespan, lifetime of a pion, charged pion, 26 nanosecond. And after 26 nanosecond, it decays and makes some other particles, okay? It decays after 26 nanosecond. So it was found experimentally that after traveling a distance of 17.4 meter, how much? 17.4 meter, after traveling this much of distance in the laboratory, inside the particle accelerator, after traveling this much of distance with a velocity of 0.913 c. C is here velocity of light, which is equal to 3 into 10 to the power 8 meter per second, that is known to you. So this much of velocity, okay, means 91.3% of the velocity of light. This is tremendous velocity, and this velocity is comparable with the velocity of light. There is almost no difference between the velocity of light and the velocity of this particle, means pion particle, okay. So it was observed experimentally that after traveling this much of distance with this velocity, pion decays, okay. Then what was the time taken by the pion? It is equal to time divided by, it is distance divided by velocity. So distance was how much? 17.4 meter, and velocity was this much. If you put the values of this d and v, you will get 63.7 nanosecond. So calculation gives you this much result, 63.7 nanosecond. And experimentally it was found, before this experiment, another experiment was done, and there it was found that average lifetime of charged pion is 26 nanosecond. So you can see that this 63.7 nanosecond, it is much greater than 26.0 nanosecond. If you take the ratio of these two, means 63.7 divided by 26.0, you will get almost 2.5, almost 2.5. So there is much difference between these two times, okay. That means there is some problem associated with this experiment. What is the problem? Means the idea about time, there is problem. Problem is there. According to Newtonian physics, whatever the concept we use about time and space in most of the cases comes from the ideas of Newton, or comes from the ideas of Newtonian physics. Newtonian physics means Newtonian mechanics, okay. So there time was considered to be absolute, and we can see that in this experiment time is not absolute. It depends on the reference frame. It depends on the speed, okay. Time is not absolute. This thing we have found by doing this experiment, by conducting this experiment, we have found this result, that time is not absolute. When it is moving, time is different. When the pion particle is moving, time is different. And when it is at rest, time is different. Where are the differences? When it was moving, time was 63.7 nanosecond. And when the pion was at rest, time was 26 nanosecond. So at rest and in motion, times are different. That means time depends upon the motion. Can you conclude this way? Yes. This was the conclusion of Albert Einstein. Time depends upon the velocity. Next, experiment remains the same. By using that experiment, one more thing will be discussed in this lecture, that is length. We have idea about length. If you are given a scale, measuring scale, okay, or measuring tape, and if you are given 2 points, you can easily measure the distance between the 2 points, linear distance between the 2 points you can easily measure by using the scale or by using the measuring tape. Same thing was done in the laboratory. First marker was kept at the position when the pion was at rest. There was kept the first marker, and second marker was placed at the position when the pion particle starts decaying. And the distance between them was measured. It was 17.4 meter. You know that thing. Okay, in that experiment it was found. But suppose the spelling mistake is there, Length. Anyway, GTH. It is length, okay. So anyway, concentrating on this, velocity was how much? Velocity was 0.913 c, right? And using average lifetime of that pion particle, we found that this is the lifespan of a pion particle. So, suppose when the pion particle was moving inside the accelerator, particle accelerator, an observer was moving with the pion particle. So, how much length that observer would observe? It will be equals to velocity multiplied by the time taken. So, velocity was how much? Velocity was 0.913 c, and time taken, I have written here 26 nanosecond, not 63.7 nanosecond, 26 nanosecond. Why? Because since the observer was moving with the pion particle, means with the pion, so relative velocity between the pion particle and the observer was how much? That was 0, because the observer was moving with the pion particle. So relative velocity between the pion particle and that man, means that observer, was 0. Am I right or wrong? Say you are traveling inside a train. Train is moving with certain speed. But what is the relative velocity between you and the train? You are sitting on the seat, okay? So relative velocity between you and the train is 0. Means with respect to you, train is not moving, and with respect to the train, you are not moving. Similarly, here we are saying that if an observer is moving with the pion particle with the same speed in the same direction, okay, then relative velocity between the pion particle and the observer is 0. Since it is 0, therefore, for that observer, what is the lifetime of the pion particle? It is 26 nanosecond. Because the pion particle is at rest with respect to that observer. So, using that value, if we calculate, so we will get how much length? We will get this velocity multiplied by the time, which is equal to 7.1 meter. But for the observer who is standing inside the laboratory where the particle accelerator is kept, with respect to that observer, the length was how much? It was mentioned here, length was 17.4 meter. So we can see that there is a difference between these two lengths. That means, how did we calculate all these things? Because Newtonian mechanics was in our head. In our, not head, brain, I should rather say brain. Newtonian mechanics, the concept of Newtonian mechanics or Newtonian physics was in our brain. And using those concepts, we have calculated, and we can see the discrepancies. Okay, we can see the discrepancies. How these discrepancies are coming in the experiment or in reality, that thing will be discussed in another video. Here in this video, just I discussed that there is some problem with our previous concept. Okay, again, once again I want to mention the same thing, that still we are using the previous concept, that is Newtonian mechanics or Newtonian physics. Still we don't face any problem, because in most of the cases the velocities or the speeds associated with our daily lives are much smaller than the speed of light, and that's why we face almost no problem. But for such cases, in case of particle accelerators, the speed is so much high. Speed of the fundamental particles are so much high, the velocities are comparable to the velocities of light, means velocities are near to the velocity of light. So in those cases, you cannot ignore the differences. But in our daily lives, we can easily ignore the differences. Okay, in my next video, I'll discuss actually what should be the procedure, what should be the method to calculate the actual length, to calculate the time, and whether those things are relative or not, whether those things are really absolute or not. Okay, I'll discuss in my next video. In a single video it is not possible, and if I make lengthy videos, then in most of the cases viewers won't watch the full length video. They won't watch. I know this thing. I have an experience of this. Okay, short videos are good. Okay, if you are a beginner of this subject, then just you watch this video and then think over this. Okay. So this is the end of this lecture. Thank you for watching this video.